This is Algebra Lesson 7-5, Rational Exponents and Radicals. Now, in this lesson, you will learn the relationship between radical expressions and expressions using a rational exponent. Two important vocabulary words. One is called the index. That's the number in the crook of the radical sign. The index gives the degree of the root. For example, if I had a cube root of something, my index number would be a 3. So the cube root of 64, the index number is a 3. A radical expression is an expression that contains a radical, like the square root of 6 or 2 square roots of 3. Now you can interchange rational expressions and radical expressions. So you can interchange rational expressions and radical expressions, and that's what we're going to be working with a little bit today, being able to go back and forth between the two, and also reducing radicals. So it says you can use rational exponents to represent radicals. So if you look at the nth root of a, my index number here is n, my radical sign is the root symbol, and the radicand is what's underneath that root symbol. Okay? The number underneath the radical sign, a, is the radicand. The number in the crook of the radical sign is the index, and the index gives you the degree of the root, which is kind of important. Now remember, we learned earlier that if we knew that 5 squared is 25, okay, because 5 times 5 is 25, so that therefore the square root of 25 is 5. Therefore, 25 to the 1/2 power has to equal 5. And it seems a little weird, but that's true. If 5 squared is 25, then 25 to the 1/2 power, I'm asking myself what number squared is equal to 25, and that's 5, so 5 to the 1/2 is equal to 25. We learned that earlier, and so we're going to expand upon that today. So we're going to learn how to simplify radical expressions. A radical expression is simplified if the following is true. The radicand has no perfect square factors other than 1. So if you get the square root of 9, that's not simplified because the square root of 9 would be 3. The radicand contains no fractions, so there's no fractions underneath the radical sign. And no radicals appear in the denominator of a fraction. So you can simplify radical expressions using multiplication and division properties of square roots. Since when a is greater than or equal to 0 and b is greater than or equal to 0, the square root of a times b is the same thing as saying the square root of a times the square root of b. So the square root of 48 is the same as saying the square root of 16 times the square root of 3. Well, the square root of 16 is 4, and square root of 3, there is no perfect square, so it's just 4 times the square root of 3. So we're going to learn how to simplify radicals today, which is really quite an important skill that you're going to use throughout your career in math. You're going to use it a ton in geometry. So this is going to be an important lesson for you. One of the easiest ways to simplify radicals is to break down the numbers down into primes and then pair up any identical prime numbers. For example, the square root of 32. Okay. It's, you could say that the 16 times 2 is 32. And say, oh, I know that the square root of 16 is 4, but some people aren't going to think clearly that way. So it's much easier for me to explain to people that sometimes it's just easier to look at this and factor it, like we used to factor things when we were younger, when we had to do greatest common factor and prime factorization. So if I break this down, I know this is 4 times 8. 4 is 2 times 2. 8 is 2 times 4. And 4 is 2 times 2. My index number is a 2, because remember, if it's not expressed, a square root has a small little 2. Right? They just don't put it there. They don't start putting the index number in until you have a 3. So I need groups of 2. I need to pair up everything that comes in groups of 2, like shoes and socks. If you go to the store and buy a pair of socks, you hope you get 2 socks. If you go to buy a pair of shoes, you better get a left shoe and a right shoe, otherwise you're going to be a little disappointed and one of your feet are going to be cold. So I'm going to pair up this 2, and I'm going to pair up these 2. This stays, because it doesn't have anything to pair up with. Anything that pairs up, you can take one of them. 2 people go out on one date. So out of this, I took out 1, 2 from the first pair. I took out a second 2 from the second pair, and I'm left with whatever is left over that didn't pair up gets multiplied back together and put back underneath, which is the 2. So 2 times 2 is 4, so this is 4 square roots of 2, which is exactly the same thing I would have gotten if I would have recognized that the square root of 32 is equal to the square root of 16 times the square root of 2, because 16 times 2 is 32, and the square root of 16 is 4. 4 square roots of 2. Some people will figure it out much better the way I did it the second way, and some people figure it out much better the way I did the first time. Because I get a lot of people who don't understand. They look at the square root of 126 and they're like, I don't know what perfect square times something equals 126. And that's where breaking it down into primes is much easier. Okay? I know that 126 is even, so that I know it's divisible by 2, so it's 2 times 63. 63 is 9 times 7. Okay, and 9 is 3 times 3. So I pair up my 3. 7 doesn't have a pair, it's prime. 2 doesn't have a pair, it's prime. So they stay underneath. Whatever gets paired up, one of those things comes out. So I get 1 3 that comes out. Whatever does not come out, whatever does not get paired up, gets multiplied back together underneath. So the 2 and the 7 get multiplied back together underneath. So I have 3 square roots of 14. And some teachers will just refer to this as 3 root 14. They won't actually say square root, and they won't say the root index until they get to cube roots and fourth roots and fifth roots. All right, 180. Okay. I'm looking at this going, I know this is 18 times 10. It could be anything. I could do 2 times 90. I could do, 5 times whatever. Whatever two numbers you can multiply together, they equal 180. I'm looking at this going, oh, okay, that's 18 times 10. 18 is 3 times 6, and 6 is 2 times 3. 10 is 2 times 5. So I have a lot of numbers here. I can pair up these 2 3s. I can pair up these 2 2s. Okay, and I'm left with a 5. That's the only thing that is a prime number that did not pair up with anything. So what comes out? One of the 2s and one of the 3s. What stays underneath? The 5. So this would be equal to 6 square roots of 5. Okay, the more you do these, the better you get at them. The better you get at them, the more things you can learn about how to deal with them. Now, the first 3 problems didn't have anything on the outside of the radical. Now we have numbers on the outside of the radicals. The numbers on the outside of the radicals just means I'm going to multiply 3 times the square root of 675. Just means it's multiplication. Since it's 3 and then the square root symbol, they don't have to put the multiplication symbol, kind of like 3 times x, doesn't have to have the dot between the 3 and the x. So I'm going to attack this one just like I attacked the other problems. I'm going to see what I can do, and I know this ends in a 5, so I'm thinking of dividing it by 5. So 675 divided by 5 is 5 times 135. 135 ends in a 5, so I know it's still divisible by 5, so that's going to be 5 times 27. 27 is 3 times 9, and 9 is 3 times 3. So I've broken my problem all the way down. I'm going to pair up the numbers. I can pair up a group of 2 5s here, 2 3s here. This 3 gets left underneath. So I pull out a 5. I pull out a 3. I have to multiply it by the 3 that was originally in the problem. Don't forget that original 3. So I have 3 times 5 times 3. Square roots of, the only thing that's left underneath the square root is a 3. So 3 times 5 is 15. 15 times 3 is 45. So I have 45 square roots of 3. Number 5 says 2 root 54. Okay, 6 times 9 is 54. 6 times 9. 6 is 2 times 3. 9 is 3 times 3. The better you know your multiplication tables, the happier you'll be with this chapter. So 3 times 3, that pairs up. These do not. So the 2 comes down because it was originally outside. One of the 3's comes out right there. And we're left with the 2 and the 3 that didn't come out. So 2 times 3 is 6 roots of 6. So 2 roots of 54 breaks down to 6 root 6. Number 6, 7 square roots of 360. All right. Well, 360 for me is 36 times 10. 36 is 6 times 6. I am not going to break that down to 2 times 3 times 2 times 3 because it's 2 pairs. 2 numbers that pair up, so I don't need to. Okay, and 10 is 2 times 5. So my 6 comes out. It gets multiplied by that 7 I already had. So 6 times 7. And underneath the radical, we have the 2 and the 5. So 6 times 7 is 42. 2 times 5 is 10. So 7 square roots of 360 breaks down to 42 root 10. Now we can also multiply. Okay? Multiplying two radicals, you just have to remember that the square root of a times the square root of b is equal to the square root of ab. So you simply multiply the whole number parts together and the radical parts together and then simplify. So if I have, like problem number 7 here, the square root of 8 times the square root of 32, okay, that's going to be the same thing as saying the square root of 8 times 32. Now I could multiply those together, but since I need to simplify this, if I multiply them together, it's going to make a bigger number that I have to simplify, and I'm going to have to undo the multiplication that I just did. So I just tell myself that I'm going to multiply it together, and then I just break it down. 8 is 2 times 4. 4 is 2 times 2. 32 is 4 times 8. 4 is 2 times 2. 8 is 2 times 4. And this 4 is 2 times 2. I have a lot of 2's here, don't I? Okay. So if I pair this up, I've got a pair of 2's here. I got a pair of 2's here. I have a pair of 2's here. And a pair of 2's here. Everything pairs up, so everything comes out and there's nothing left inside. So if I take one of each one of those numbers out, I have a 2 times 2 times 2 times 2, which gives me 2 times 2 is 4, times 2 is 8, times 2 is 16. And some people may have looked at that and said, well, you could have done that a lot easier. Yes, there's a bunch of different ways you can do that. The more familiar you get with simplifying radicals, the better you can get at finding some shortcuts. But for right now, we'll just leave that problem like that. Now, if we look at number 8, remember what I said, whole number times whole number, radical times radical. So 4 times 2, square roots of 10 times 90. Well, 4 times 2 is 8, square roots of 10 times 90. So I need to break down the 90. I'm going to break it down to 10 times 9, all right, because that's 90. This pairs up. 9 breaks down to 3 times 3. Those pair up. So I can take out a 3. I can take out a 10. And I already have the 8 on the outside. So this is going to, the 8 that was already there times the 10 I took out times the 3 I took out. Okay, which is end up to be 240. So sometimes when you multiply or simplify, you get down to back to a whole number. All right. Let's take a look at 2 square roots of 3 times 3 square roots of 2. So whole number part times whole number part. That would be 2 times 3. Radical times radical, 3 times 2. 2 times 3 is 6. 3 times 2 is 6. This breaks down to 6 root 6. Now number 10 here, if I have 4 square roots of 3 quantity squared, that's the same thing as saying 4 square roots of 3 times 4 square roots of 3. Or we could remember our property of exponents, which says we need to distribute the exponent. So I distribute it to the 4, and I have to distribute it to the square root of 3. Okay. So let's take a look at what happens when I multiply 4 square roots of 3 times 4 square roots of 3. 4 times 4 is 16. Square root of 3 times the square root of 3 is the square root of 9, which is just 3. And 16 times 3 is 48. One thing that you need to recognize, if I have the square root of 3 and I square it, squaring undoes a square root. Square rooting undoes a square. So this cancels out that symbol, so you get 3. So the square root of 152 squared is just 152. The square root of any number squared, the square root and the square cancel each other out. You're just left with the number, which is kind of a cool thing. All right, now the division property of square roots states that for a being greater than or equal to 0 and b being greater than 0, the square root of a divided by b is the same thing as separating them and making them the square root of a divided by the square root of b. Okay. Sometimes it's nicer to leave them separated, and sometimes it's nicer to put them together. If you look at number 11 here, I have the square root of 144 ninths. 144 does not is not nicely divisible by 9, I don't think. Actually, it is. Okay. So let's do this. If I have 144 ninths, if I take 144 and I divide it by 9, I get 16. So that becomes the square root of 16. And what's the square root of 16? Well, that is 4. Okay. So we could be done right at that point. Now, if I look at number 12, 16/25 does not break down nicely. So in this particular case, I'm going to separate the square roots. I'm going to separate this as the square root of 16 over the square root of 25 because my brain says, hey, the square root of 16 is 4 and the square root of 25 is 5, and now I am done because I have no radicals in the denominator, I have no perfect squares, and I have nothing that can reduce any further. So I have reduced and simplified my radicals. Now these two ended up to be really nice problems. That doesn't always happen with division. When a radicand in the denominator is not a perfect square, you may need to what they call rationalize the denominator to remove that radical sign. To do this, you must multiply the numerator and the denominator by the same radical expression. You want to choose an expression that makes the radical in the denominator a perfect square. Okay? And it also might be helpful to start by simplifying the original radical in the denominator first. So let's take a look at number 13. If I take a look at number 13, I have the square root of 2/3. Well, 2 is not divisible by 3, so I'm going to break this down to become the square root of 2 divided by the square root of 3. Now I can have the square root of 2 in the numerator all day long, but I cannot have a square root in the denominator because it's what we call an irrational number, and you cannot have an irrational number in your denominator. So you must make it a rational number. And the easiest way to make it a rational number is to multiply it by a fancy form of the number 1. Now, if I looked at the square root of 3 and I said, how do I get rid of that square root? Well, didn't we just talk about how a square undoes a square root? So if I looked at this and I said, well, if I multiplied this by the square root of 3 over the square root of 3, that's a fancy form of the number 1. So really, I'm not changing my problem because anything times 1 is just 1. The square root of 3 divided by the square root of 3 is still 1, just like x divided by x is 1 and 3 divided by 3 is 1. But what happens here is if I have a square root of 3 times the square root of 2 in my numerator, that becomes the square root of 6. And in my denominator, I get the square root of 3 times 3. But what is the square root of 3 times 3 or the square root of 9? That would be 3. So I get the square root of 6 over 3. Now this does not simplify any further. Don't get into the habit of thinking, oh, I can divide this 3 into that 6. The only way you can do that if both numbers are underneath the radical or both numbers are outside of the radical. You cannot simplify if one number is underneath a radical sign and the other number is not underneath the radical sign. So the square root of 2 over the square root of 3 reduces this to the square root of 3, or the square root of 6 over 3. Number 14, 3 divided by the square root of 12. Now there's two ways to do this. One's I consider to be much more difficult than the other. I look at 12 and my brain says, wow, that's 4 times 3. Okay, I know that 4 is a perfect square, so I'm going to simplify the square root of 12 first. Since this is 4 times 3, this 4 becomes 2 times 2, so that's 2 root 3. So now I have 3 divided by 2 square roots of 3. Well, I cannot leave the radical in the denominator. The 2 could be there all day long, but the square root of 3 cannot. Since 2 is multiplied by the square root of 3, not added or subtracted, all I need to get rid of is the square root of 3. To do that, I'm going to multiply by a fancy form of the number 1. So I'm going to multiply by the square root of 3 divided by the square root of 3, just like I did on problem number 13. So in the top, 3 times the square root of 3 becomes 3 square roots of 3. And on the bottom, the square root of 3 times the square root of 3 is 3. So I get 2 times 3, which is 6. So I get 3 square roots of 3 over 6. Now I can simplify because both the 3 and the 6 are outside of the radical symbol, which means I can take 3/6 and reduce that just like I would normally reduce a fraction. So 3 over 6, 3 goes into itself once, and it goes into 6 twice, so this becomes the square root of 3 over 2. And I have simplified that radical, and there are no radicals in the denominator. Okay, let's look at number 15. If I look at number 15, I've got the square root of 6/32. Well, 6 over 32 does reduce. 6 doesn't divide into 32, but I know they're both divisible by 2. So if I simplified this, I could get this as to be, if 2 divides into 6 3 times, 2 divides into 32 16 times, Okay, which this is now nicer because now I have the square root of 3/16, which is the same thing as saying the square root of 3 over the square root of 16. The square root of 16 is 4, so this becomes the square root of 3 over 4, and I don't even have to rationalize the denominator. I'm done at that point in time. Right? So this is just dealing with radicals. And we can deal with a lot of things besides just radicals, but this is just one of the many topics that we can do when dealing with radicals. Okay? And we can simplify radical expressions by finding like factors, just as when simplifying powers with rational exponents. Okay, so let's take a look at something else. Okay, let's find some roots. What is the simplified form of each expression? The cube root of 125 and the fourth root of 16. Okay, the cube root of 125. One way I could look at this is I could say, okay, the cube root of 125. We can simplify this kind of like square roots, except for instead of needing groups of 2, we now need groups of 3. Well, I know 125 is 5 times 25, and 25 is 5 times 5. I need groups of 3 to take anything out, so the cube root of 125 has to equal 5. Okay. I could look at this and do the same sort of thing with this. I could say, okay, the cube root of 125 is a lot like saying 125 to the 1/3 power. Okay. This would be method 2 for the same problem. So I would say if I have 125 to the 1/3. Okay. And you might say, well, how do I do that? Well, remember, 125 to the 1/3 is like saying what raised to the 3rd power equals 125. Okay. Something to the 3rd power equals 125. Well, I know that 5 to the 3rd power is equal to 125. Okay. So I know that 125 to the 1/3 is equal to 5. That's the second method. Let's look at problem number 17. Very similar. The fourth root of 16. By method 1, I'm just going to break it down into what I know. Just break it down into primes. 4 times 4. And 4 is 2 times 2. And 4 is 2 times 2. Now I need groups of 4 to take anything out. So there's 4 2's. So I can take out one group of 2's. So I take out 1 2. So the fourth root of 16 is 2. In the second method, I'm looking at the fourth root of 16. And I'm going, okay, 16 to the 1/4. Okay. And I might say, well, what to the 4th power equals 16? 16 is equal to 2 to the 4th power. So I'm taking 2 to the 4th raised to the 1/4, because 2 to the 4th is equal to 16. Remember, a power raised to a power is multiplied, so that becomes 2 to the 4 over 1 times 1 over 4, which is just 2. Notice I get the same answer using either method. Whatever method makes more sense to you is the method I would definitely work with. However, okay, if you actually understand the second method that I'm working with here, you'll understand how to change things from rational exponents to radical exponents and back and forth. So you can also write an expression that has rational exponents like 2/3 in radical form. Okay, so like 8 to the 2/3 is the same thing as saying 8 squared times 1/3. Okay, and remember, a power raised to a power is multiplied. So that would be just like saying the cube root of 8 squared. Or 8 to the 2/3 is 8 to the 1/3 times 2, which is also the cube root of 8 squared. Okay, which basically means that it doesn't really matter where the square goes. Okay, notice these two expressions are equivalent. The cube root of 8 quantity squared, okay, is the same thing as the cube root of 8 squared. Excuse me, not those two expressions. This expression and this expression. Oops, this way. Okay, so all three of these are the same. It doesn't really matter how you write them. So if the nth root of a is a real number and m and n are positive integers, then a to the 1 over n becomes the nth root of a, and a to the m over n becomes the nth root of a to the m. Okay, which means if I had 4 to the 2/3 power, that's the same thing as saying the cube root of 4 squared. Okay, this becomes the index number, this becomes the exponent. That's what it's saying. Don't let it get you all confused with all the extra words that they put in there. So what are we going to do? We're going to convert from rational form to radical form. If something has a fractional exponent, it's called a rational exponent. So x to the 3/5 is what we call rational form. We need to change it to radical form. So we need something root something. Well, the number on the denominator becomes your index number. The number in the numerator goes on your variable. So this is the 5th root of x to the 3rd. If I have 64b to the 3/4, okay, this is the 4th root of 64b cubed, which is a little bit more difficult to work with. So I'm going to think of this. Okay, I know that 64 is equal to 4 to the 3rd. 4 times 4 times 4. Okay, so if I wanted to, I could make this 4 to the 3rd b all raised to the 3/4 power. So that would be 4 to the 3/1 times 3/4, and b to the 3/4. So this becomes 4 to the 9/4, b to the 3/4, so we have 4 to the 9/4, b to the 3/4. All right, so since both of those are the 4th power, that would be the 4th power of 4 to the 9th, b to the 3rd. Okay, so 4 to the 9th means I have 4 9s, or 9 4s. So 1, 2, 3, 4, 5, 6, 7, 8, 9. I need groups of 4. So there's one group of 4. There's my second group of 4. So 4 times 4 is 16. So this would equal 16 on the outside. Based on what we were doing with the square roots, we're going to do the same thing with the 4th roots, but instead of grouping up pairs of 2, I'm grouping up groups of 4. So 4 times 4 4th roots, I have 1 4 left over, and I have 3 b's left over. So 4 times 4 is 16, so this becomes 16 4th roots of 4b cubed. And be very, very careful to make sure your 4th root is the index number and not an exponent to a different number. Okay, that one was a tough one. I doubt I'll ever give you problems that are that difficult in your homework, but hey, if you can do this now, you'll be in much better shape when you get into Algebra 2 and in geometry. All right, number 20 says 18b to the 1/4. The only thing taken to the 1/4 power is the b. So the 18 stays on the outside, so this becomes 18 4th roots of b. And that's a terrible 4. It almost looks like a 9. Make sure your 4s and 9s look definitively different. There we go. All right, so if we can change something to radical form, we should also be able to change it to rational form. If I have the 5th root of a to the 3rd, okay, we're going to undo what we just did. Remember, this is going to be the denominator. This is going to be the numerator of the fraction. So we're going to have a to the 3/5 power. Okay, the cube root of 27c squared, that's the same thing as saying the cube root of 3 cubed c squared, because 3 times 3 times 3 is 27. So I have 3 to the 3/3, c to the 2/3. Well, 3 to the 3/3 is 3 to the 1st, which is 3. So this becomes 3c to the 2/3 power. Now, there are other ways to do this, but this is just one way. And you're probably going to encounter a couple of other ways before you're done with your mathematical career. Whatever way makes more sense to you is probably the way that I would do. Okay. All right, if I have the square root of 2c to the 4th, that's the same thing as saying 2c to the 4/2, because remember, if the index number is not indicated, it's a 2. Okay, so 4/2 is the same thing as saying 2. So this becomes 2c quantity squared. If I distribute that 2, that becomes 2 squared c squared, which is just 4c squared. Now I know I threw an awful lot of material at you in this lesson, but it was all important stuff. Not all of it is in 7-5 in your textbook, so I would suggest you don't rely just on your textbook, because quite a bit of what I've done is not in 7-5 in your textbook. I threw some other stuff in here because it made sense and it went together well. All right, your closure question for this lesson. Write a rule for multiplying two radicals with the same radicand. A couple of vocabulary words in this one. So write a rule for multiplying two radicals with the same radicand.